So Mellanox is one of the leaders in the interconnect solutions in the world. We provide silicon, switches, adapter cards, as well as software packages that some of them are contributed to the community, and cables, and we provide high end-to-end InfiniBand and Ethernet solutions. So you're looking at three areas of acceleration on, I would say, the big data solutions. One is the analytical portion. We kind of segregate that one aside. The storage and the distributed storage. And we go one by one. The reason to do data analytics acceleration is that people are trying to deploy systems today, and what they find out that they have a huge gap between expectation and real deployments. Sometimes the difference is 50% or 100%, depends on the way you look at it, and we try to close that gap. We try to find out ways to utilize the CPU better, something that most of those applications find out to be challenging in the terms they are written today. So the first one we look at is Hadoop. Definitely the most dominant application in the market. Previous speaker was also speaking a lot of Hadoop and Hdfs, and we'll see what we did around this one. So the first project we took was UDA. We just released the latest version last Thursday. It's open source project on Google Code. You can download it, change it. There's already, I think, 6 or 7 clones to that code. And people analyze data faster. And the reason they can do it is that we take and leverage the RDMA capabilities that we have in the cards in order to move the data between map output files and the reducer side. So if your workload is based on map reduce and mainly reduce side, you're able to leverage those capabilities. Today we have pushed into the trunk to 2.0, so Yarn, and 3.0. We have patches on that same Google code for Apache 1 and all the main distributions that are out in the market. We are doing putting a lot of effort to put also a patch to the 1.x, but it's going to be a challenge at this time in this market. The idea is that the Hadoop framework, the analytic portion of it, has a serialization process in it. So you have to do the mapping, then you have to do the shuffle and merge, which move the map output files into the reducer node if it's not on the same node, and then you have to start to do your function of reduction. And there's a big serialization process and a stop point, which you have to wait for all the merging to happen. With the UDA with the UDA approach, you can do it a little bit different. So the mapping side didn't change, because if you change the mapping side, you actually change your function. But once the mapping is completed, we start doing shuffle and merge. So we take small portions of that information of the map output files and do shuffle and merge between the nodes. What it gives us the ability is to do reduction immediately as we shuffle and merge the information. So we have a way to parallelize the reduction with the shuffle and merge. If we look on the architecture of building that solution, we actually take and put a small shim layer inside the map output file, the main map task, that announces that we have a map output file completed. We use the RDMA portion to take only a small portion of that information, of that map output file, usually 1 kilobyte or 2 kilobytes of information, and move it to the designated reducer. The reducer gets the information through the RDMA client, and we do merging in C code, which is much more efficient. This is part of the levitated merge algorithm that was developed together with Auburn University. Now all the merging is done at C in memory of that reducer side, and reducing the execution time on that specific map output file. The results that we see today are around 50% reduction of the total execution time. So vanilla versus the UDA portion, which is the same distro, just with the UDA plugin inside of it, gives you 50%. This one is old because it was yesterday, but this morning I got another email from the team that does the benchmarking, and they were able to reduce another 15% of that execution time just by tuning the right knobs in the MapReduce framework. So get more memory into the UDA portion of the solution, and actually doing different ways of slow starts on the output files from the map output files. This one is used Greenplum Hadoop distribution. It's a 16-node Westmere machine. All the information is out there on the Google code as well. Speaking about Intel, Intel has a nice benchmark solution that's called HiBench. And we want to try to understand more on the analytic portion. So using clustering algorithms, search, and sort, we find out that if we take and see on a slow network what happens and how fast network can help, we sometimes see a solution that can give you 100% much more throughput. This is even still without no RDMA. When we put the RDMA on it, we expect to see similar expectation to this one. So taking off the CPU, all the transaction portion of the information, and move it down to the card. So the initial results show us there is benefit in opening those pipes. So running more and more solutions over RDMA, we find that's going to be even more throughput capabilities into the analytic portion of the solution, even without the storage yet. Most of those solutions are either I/O bound, meaning the network bound, or CPU bound. In both cases, what we find out that that's a lot of spinning cycles that are not used in the CPU for doing the actual transaction and moving the data between the nodes. Same idea with Cassandra. So Cassandra is a columnar NoSQL database that many enterprises use for their big data solutions. Same idea. Open the pipes. Find out a way to leverage those CPU cycles that you have in the machine, not to do networking, but to actually do the processing of the data and answering the query. There are two items to look on Cassandra or databases as a whole. The first one is the actual latency to get the understanding of where the data is or what's the query results. And the second one is the dispersion of solutions. So if you look on the amount of data that you send queries in and out, there's a variation of the answering time. Sometimes there's a big trail of, to the right of information when you get the actual results out. Well, we found out that using RDMA, we're able to cut that dispersion by 50%. So now your system is much more predictable. You know exactly how much data you're going to get and how much time it's going to take it to get there. Once again, those are initial results. We're trying to harden the code in order to provide better solution to the market. Same idea we're going to have here. Open source the solution, push it down the community, and into the main trunks of the Cassandra project. So that portion was on the analytical side. When we look on the storage, and we look about the great things about Hdfs, we find it's a block storage, and people like it. Easy to manage. Easy to manage the size. Yeah. Reliable. Yeah, you have 3 replication of the data, which is awesome for the disk drives vendors. And everything is open source, and you can do whatever you want. The less fun things about it, single point of failure. Everybody loves it, right? You put it there, name node goes down, you cannot reach any data. Goodbye. Yeah, it's easy, but it's not cheap. So people tell you that commodity servers, blah, blah, blah. Each node costs between $7,000 and $18,000. Depends on how many disks you put in and what's the technology. So it's easy to put it in. It's going to cost you a fortune in the pocket. Small files. As my previous speaker said, no good. You have small files, it's going to block all the capabilities in the cluster. Manage. Try to manage a large 1,000, 2,000 node Hadoop cluster. Not fun at all. Nodes are coming in and out. Deprecation is extremely hard. If you want to bring down a node, it's going to cost you between an hour or 2 for all the replication to take place. And the last thing, try to drink from the fire hose. When the data comes in, it's going to be hard. Tons of tools to get the data in and out from a Hadoop cluster. Scoop, Flume, we can keep on throwing names out there. So the solution is kind of hard. So we try to find our way in that market, which is very, I would say, fragmented. And look on when you build a Hadoop cluster or a Hdfs cluster, how can we help you? So first, think about your growth rate. How much data you really need. Is it a really big data problem? what's the cost? So where do you go, SSDs, spindles, or a kind of a mesh between them? How much time are you going to have the data in? Some people don't think about it. So do you delete files or you don't delete files? Do you need real-time application? Some applications become, Hadoop becomes real-time, and people want to use real-time application on top of Hadoop. It's kind of a challenge. And what's the value of that information? Can you really spend $18,000 on a box for data that's practically garbage in and garbage out? So we kind of work together with Ohio State University to find ways to bring more value into the Hadoop framework using RDMA. So using RDMA capabilities, we are able to double the throughput of a Hdfs cluster. So if you move a 6 gigabyte file, you can do it twice as fast. The blue line is IP over IP, so it's the same InfiniBand network, but just using the IP version of it. And the red bars are the RDMA capabilities, or the RDMA solution on top of it. If you look on the architecture of that solution, it's fairly simple. So we didn't change anything on the TCP IP or the HTTP call to the name node. We just changed the access data into the data node itself. So you get all the metadata from the name node directly as you used to do it before, and the access is on the RDMA layer. That's the benefit of that solution. Also, the replication is taking place on the RDMA network. So there is no CPU involvement in the moving of the data between the different data nodes and the daisy chain of creating those replications. So now your CPU is not involved anymore with those replication processes. On the read side, same idea, but the replication is not in place in here. So there is no change on the metadata node access. You actually go to the name node to get the metadata and access the block on the different boxes using RDMA. Once again, taking those CPU cycles that you used to use on the TCP IP stack and save them for actual MapReduce or any other type of application you have on the cluster itself. So we go into that project again, and we try to find out if there is money in this case. So even with spindles, we found out that we can double the performance. Simple. Use SSDs, 3-4 times faster. So if you use 1 gig or 10 gig, probably you're blocking your capabilities. You want to open those pipes again. Then that's going to bring down the cost of your box, because now you can get more from a single box without investing in more CPUs, more motherboards, more spindles, or SSDs to get the same throughputs. And now to the distributed storage solutions that we're looking at. First one that we did is together with the University of the Pacific. It's based on OrangeFS. So they have a nice research called HFAA, or the Hadoop File System Agnostic API. You can plug in any Hadoop application, and it's going to think it has an Hdfs layer, but the underlying asset is going to be a different file system. Actually, any file system that you can think about. So in this case, the first project that we did was with PVFS, or its more mature version, it's called OrangeFS. And we get either on par or better performance with the HFAA solution. So if you use Hdfs with regular spindles or SSDs, or use HFAA or the agnostic portion of it, you're going to get the same performance or better one. Meaning you can now disaggregate the compute side and the storage side, the same way you think about doing it with Lustre. So you get, again, the same benefits. Lustre, the work was done with Intel today, but it's kind of, I would say, done before with Sun and Zyratex as well. So this is a work that was done by Zyratex with, I think it was Nathan Rothman did the work here, and did the math. It's going to cost you 1/3 to do it with Lustre. Yes, Lustre unfortunately have sometimes a bad reputation, but I think there is a good case for using Lustre for Hadoop environment. Economical, as well as benefit on throughputs. So we're going to see, I think, cluster more and more deployed with Hadoop file systems, as a Hadoop file system instead of the regular Hdfs. Moreover, there's a lot of academic research that already have installation base of compute nodes, and they need some type of storage to connect. Cluster becomes a natural segue for their perspective. The next one is Ceph. So Ceph is becoming, I would say, the cloud file system or the object storage. And we find it a very intriguing solution. Ceph already has an iSCSI or ICER solution inside of it or integrated. And moreover, it's going into the Linux kernel, which means easy to deploy. So we find Ceph as a very intriguing file system. We just installed that one. We tried to find out the performance side of it. So I hope to have the information today for the performance side. We were not able to complete the work there, but stay tuned. We're going to see how can we actually use RDMA and fatter pipes, like 40 gigabit Ethernet, as well as FDR InfiniBand, to push the data from a Hadoop cluster or I would say the MapReduce portion of it into the distributed storage. So there is a good advantage of, and solutions coming on Ceph. We see that solution as very intriguing in some enterprise and cloud environments. Some marketing slides. We are fully certified with Cloudera. So any Cloudera distribution you're going to use with Mellanox equipment is fully certified. So you don't expect any issues there, both on the InfiniBand as well as on the Ethernet side of those solutions. We have nice recipes on our website on how to build a cluster. We typically recommend at least 4 data nodes and 1 name node, etc., etc. Those solutions were tested, so we actually took those recipes and built our own clusters inside our labs using those recipes. Highly usable. We see a lot of people coming in using those recipes, asking more questions, and we constantly improve those recipes and get more and more information inside of them. So use them. It has a portion on how to deploy the UDA portion, UDA framework inside the Hadoop one. Very useful. And if you find yourself in time of trouble and you don't have the money to buy a 1,000-node cluster, we can help you. So there is a 1,000-node cluster that we built together with the EMC Greenplum, or what's going to become Pivotal in the next couple of months. And that cluster is available to anyone. So Google Workbench Analytics, put your name in, and you have access to a 1,000-node cluster, just like that. So we know that there are a lot of people using this cluster, government agencies, commercial companies as well, to try and see how Hadoop can help them. This is a 24 petabyte of storage, 1,000 Westmers, 48 gigabyte of data on each, RAM data on each one of them, as well as InfiniBand FDR all across the board. So you can come in, test drive, see what it's going to do for you, and enjoy the time using it. And with that, I thank you. If you guys have any questions, I'll be more than happy to answer them.